Good morning. I welcome you to this session of fluid mechanics. We are discussing the pipe flow problems, viscous flows through pipes, different types of losses while flowing through pipes, fluid flowing through pipes. Today we will be solving some problems which will give you a better understanding of the principles we have discussed. Now let us first see the example 1. Well, example 1, you just see, you can write also a single pipe 400 millimeter in diameter and 400 millimeter long, diameter and length, conveys water at the rate of 0.5 meter cube per second, a single pipe of this diameter and this length. Find the increase in discharge if another pipe of 200 millimeter long and 200 meter long and 200 millimeter in diameter is joined parallel with the existing pipe over half of its length. Friction factor for all the pipes is same. This problem is very simple, but this problem underlines one principle, that when we make a parallel joint of pipe, this increases the discharge under the same head difference. This is the principle which you have come across earlier also in electrical circuit, that if the potential difference remains same, that the parallel circuit always reduces the resistances. That if I use a resistance, so parallel circuit reduces the resistance. So the equivalent resistance is lower than the lowest resistance. So therefore, if another pipe of 200 meter long and 200 millimeter in diameter is joined parallel with the existing pipe, of course it depends upon the resistance of the pipe, over half of its length there is an increase in discharge, just like an electrical circuit where there is an increase in electrical current. Friction factor for all the pipes is same. This is a simple assumption given for the problem. So now problem is, there is a single pipe 400 millimeter diameter and 400 meter long, and it discharges. This is the first condition. And second one, and another pipe 200 meter long and 200 millimeter diameter is joined parallel, half of its length. Find the increase in discharge. Very simple problem. The problem is like this. This H1 is the, this is the first pipe, 400 meter length and 400 millimeter diameter. That means this is 400 meter length and this diameter is 0.4 meter. And this length is, this pipe length is, this length, half of its length, this length is 200 meter. And this diameter is 0.2 meter. So this is joined. Now in the first instant there is no other pipe, so single pipe which conveys 0.5 meter cube per second. If I write the frictional formula, what I first assume, that H1 is the inlet head and the outlet head, which should be same for the parallel pipe, is H. H1 minus H delta H. So delta H is the driving potential or driving head for the flow. So when the single pipe was there, I can write delta H is FL by D, V square by 2G. This is the V, because V is always Q by A, which is pi D square by 4. So always for a pipe circular cross section, this is the value of V. So when the Q is 0.5 meter cube per second, I just substitute this value, from which I get the friction factor value. So this I have already seen earlier, always 8F by G pi square coming. So from which I get the values of delta H. Sorry, friction factor is not found because delta H is not given. So from the friction equation for a single pipe, I make a relationship between the head causing the flow with the friction factor in this fashion. Now for parallel pipe system. Now what are the main principles of parallel pipe system? I told, very simple thing, common sense, that the total flow, now when the parallel pipes, when another pipe is added, so this flow rate is changed, this 0.5 meter cube per second is changed. So a new flow is set up to the entire system. Let us consider this new flow rate is Q dot, which is now coming from the main source, that means from here, inlet plane, which is getting divided in the two pipes. So if I consider Q1 dot is the flow rate through this pipe, 400 millimeter diameter, and Q2 is the 200 millimeter diameter pipe flow rate, then the sum of this is Q dot, continuity. Now if I write the friction equations for both the parallel pipes, I told you earlier how we found out the flow distribution, by writing the friction equation for both the parallel pipes between the two junctions. So what we can do, that the head loss between this point and that point and between this and this through this path is same, because head at these points are same. So through this path and through this path. So this head is same, so head loss is same. That means head loss is equated for two pipes, parallel pipes. So for this pipe F L by D, this is 200 meter length, 4 Q1 dot by, but the velocity, average velocity in this pipe related to the flow rate in this pipe, which is Q1 dot, is equal to the head loss via this parallel pipe is L by D. The average velocity is related to the flow rate through this pipe, that is Q2 dot 2G. So if we solve it, we get a relationship Q1 dot by Q2 dot 2 to the power 5 by 2. It will everything cancels. F same 1 by 2G, 1 by 2G, pi, 4, 4. So only 0.4 and 0.2. So one is twice of the other. So 2 to the power 5 by 2, this comes this. Therefore, Q1 by Q2 ratio is there. So Q1, Q2 can be expressed in terms of Q. One is 5.66 by 6.66, that is the Q1, larger one. Another is 1 by 1 plus 5.66. So simple algebra of primary school. So we can find out that Q1 in terms of Q, Q2 in terms of Q. So therefore, the flow rates are known in terms of a single flow rate Q, that is the main flow coming from this. So now our job is to find out this Q. So this Q can be found out by writing the friction equation in any hydraulic path. Either you take this path, the main pipe via this pipe, or you can write the hydraulic equation via this path. That means either you write the Bernoulli's equation between this point and this one via this path, main pipe, or this point and this point via main pipe and then this parallel pipe. So any of the pipes, so that if you write the Bernoulli's equation, means the friction equation, because delta H is FL by D, this comes from the application of Bernoulli's equation only. So if you write, then you can find out the value of Q dot. This is the trick. Now if I write via this main path, the equation is like this. Delta H, I write this via this path, H1 minus H, delta H is FL by D up to this length. The frictional loss is, this is also 200, half, this is 200, then this is 200 millimeter and 0.4 diameter FL by D V square, which is related to the main flow Q dot 2G plus the frictional loss in this part. There is no other minor losses. If minor losses are there, depending upon the geometry, we will have to take care of. If there is a fitting, we will have to take care of. But nothing is there, only friction in two parts, L by D. It is same L, same D, but the velocity is changing. So 0.85 Q dot is the velocity, because we found out that Q1 dot is this, Q2 dot. So Q1 dot is this flow, this 5.66 by 6.66 Q dot, this is 0.85. So therefore, the flow rate through this pipe is 0.85 of Q dot. So this is the flow rate. Very simple. So then that means we have an equation connecting delta H with Q dot square. But delta H was earlier found in terms of friction factor like this, because the same head difference was there when the single pipe was delivering 0.5 meter cube per second. So if we equate this, if we equate this, equating delta H for single and parallel pipe, that means 8F by G pi square into 100 into 0.45 is equal to this one. That means if we equate this one, 8F by G pi square earlier with this thing, we get simply the value of Q dot 0.54. So you see here, now the Q dot, which was earlier 0.5 meter cube per second, is now increased to 0.54. So 0.04 meter cube per second. I think this is okay. Very simple. Any question, please?
So like, won't there be entry loss?
Yes. Won't there be entry loss? This is just a problem. Now, this entry loss where? Here?
No, at the junction.
At the junction. No, nothing is told. There, if due to the bend, there will be some losses. But it is not told, so how can you do it? In practice, there will be loss depending upon the curvature and degree. How? These are practical considerations. I am defining the theoretical aspect of it. In practice, if you make a parallel pipe joint, so there will be some bend of the pipe and then pipe goes like that. So due to that bend, there will be some losses. In a problem, if that is not told, you cannot find it. In practical applications, what you will do, you will know the pipe bend, what is the angle of the pipe bend, what is the diameter. Depending upon the diameter and the angle, the loss coefficients for the pipe bends are known, then you add it. Very correct. But here nothing is told, as if two parallel line like that. So there are two parallel lines, these 2 points are same. That means we neglect this bend. losses. Very correct. There will be some loss. Definitely fluid flow go like that. Practically a pipe cannot be made parallel like that. It cannot be superimposed on that. So there will be a bend and all this. This we neglect it because of the lack of data. We are not told. That can be added. That consider a bend loss for whose coefficient is this. In that case what you will do, you will write the equation here. So you will have to add kv square by 2g if k is the loss coefficient, because bend losses and many losses are expressed in terms of the a factor k of the velocity head. So this is the loss. This is not given. So we just neglect it. All right. Okay. For example, I can explain very good that if the problem was given like that, there is a tank and there is a head. That means then the H1 is given in terms of the height. So you can consider H1 is the height of the surface from here. So this is a big tank and this. In that case, I will consider the entry loss. But here H1 is defined is the head here, just at the inlet, after losses and everything. So nothing is given here. So if the problem is posed like that, then we will use this H1 as the height, and then we will consider the losses, we will consider the entry loss. Okay. Now example 2. Water flows out of a reservoir through a horizontal pipe 500 millimeter in diameter. Water flows out of a reservoir through a horizontal pipe 500 millimeter in diameter and 400 meter long. The level of water in the reservoir is 10 meter. Due to a partial closure of the pipe at the discharge end by an obstruction, the flow velocity through the pipe is 3 meter per second and the pressure loss per unit length is 135 Newton per meter cube. This is very important data. That means in a pipe, this type of pipe, this particular case, the pressure loss per unit length is constant almost. That is why they are specifying the pressure loss per unit length in the pipe is this one. Calculate the pipe friction factor and the loss coefficient of the obstruction. So again we should think of the problem. This is another exercise problem of my book. Last one was also one of the exercise problems of my book. Water flows out of a reservoir. That means there is a reservoir through which water flows out through a horizontal pipe. From a reservoir, water is flowing out through a horizontal pipe. 500 millimeter in diameter, that is explicitly pipe geometry is known, both diameter and length. The level of water in the reservoir is 10 meter, means in this case the level is kept constant, steady problem. Due to a partial closure of the pipe at the discharge end, it is a very practical problem. That means at the discharge end of the pipe there is a valve which is partially closed, that means which controls the flow. The flow velocity through the pipe is 3 meter per second. So a valve is there or an obstruction, you consider valve is an obstruction, so that which makes the flow reduced, and in that condition the flow velocity through the pipe is 3 meter per second. And at that condition the pressure loss per unit length is 135 Newton per meter cube. What we will have to calculate for this problem? Pipe friction factor and the loss coefficient of the obstruction. So obstruction gives some loss, that means you consider the losses due to obstruction and find out what is the loss coefficient. Loss coefficient means that k, that means the obstruction loss, if it is expressed in terms of kv square by 2g, this is known as loss coefficient or loss factor. The second part, estimate the flow velocity when the resistance is withdrawn completely. That means if the valve is widely open, that means there is no resistance given, that means resistance is withdrawn completely, then flow velocity will definitely increase. So this is increase. Neglect entry loss. Yes, the problem tells neglect entry loss. This is not correct. I could have done with the entry loss also, but I have not done with that. Neglect entry loss, but account for the exit velocity here. Okay, let us see the problem. This is a reservoir. Okay, so 10 meter head, and this is a long pipe. There is a valve. First case is that now delta P by L is 135 Newton per meter cube. What is F? F is now, if you write the equation, F is L by D. Now first of all you will have to find out the friction factor from this formula. Now in this problem delta P by L is given. So I can take any length L without any entry loss, even if entry loss has to be taken into account or loss coefficient, over any length L, you know the formula is delta P or delta H, delta P by rho G is F L by D V square by 2G. GG you can cancel. So that one can find out F is equal to delta P by L into D by half rho V square. That means if I know delta P by L, pressure drop per unit length, so wherever for any length I can find out friction factor simply by this formula, that I can apply anywhere midway in between in the pipe, where delta P by, if delta P by L value is straightforward known. So this is the simplest form of a problem where F can be found out simply by this, no other loss comes into picture over any length where there is no obstruction, nothing. So D by, so this formula is written, F is equal to, this is delta P by L, delta P by L. This is D, obviously D is what? 500 millimeter, that means 0.5 meter, half rho V square. So we get straight away friction factor. Now the rest part is very simple. If I write the Bernoulli's equation between this point and this point, we get the equation 10. Bernoulli's equation, the pressure head is 0, velocity head is 0, so 10. So I take the center line as the datum. Then of course, if entry loss is there, we will have to add here 0.5 into V square by 2G. V is 3 into 3, 3 into 3 by 2 into 9.8. Actually this could have been taken into account, but the problem categorically tells that you neglect entry loss. So this case you should neglect, otherwise people will think that you have marked the formula and you have done it. So neglect the entry loss, 0.5 V square by 2G should come first, but this you neglect. So next loss is the loss due to pipe friction, that means F L by D into V square by 2G, plus when the flow comes through this is a valve representation. So there is a restriction, different types of valve is there. One type of valve, there is a gate type of thing which comes, the same gate comes like this and closes the passage. So it falls like this. So this is a restriction. So it gives a pressure drop or the head loss, whatever you call it. So this loss is expressed as K V square by 2G. K V square by 2G plus V square by 2G. This is the velocity head here, V square by 2G. So this writing is actually a typical writing for friction equation, but if one writes the Bernoulli's equation, he will write like that, 0 plus 10 P by rho G is equal to here P by rho G 0, but V square by 2G 3 into 3 into 2 into 9.81 plus the datum head is plus 0 plus all the losses encountered in the path. That means this will become fast in his case. Bernoulli's equation, modified Bernoulli's equation, we write the pressure head, velocity head, this is the sequence, conventional sequence, datum head, potential head plus the losses in the downstream side point or downstream side section plus the losses if the flow is viscous. That means a modified form of the Bernoulli's equation considering the viscosity of the fluid. But in conventional friction equation, people go on writing as if he is following the path like that. First the fluid encounters this loss, entry loss, then the friction loss, then this loss, plus it is having a velocity head. That means a simple energy balance, energy accountability. Whichever way you look into the problem, the equation remains same. That means this side 10 is equal to the velocity head plus HL. If one tells that I will write the equation far ahead when fluid velocity is not there, for example if it was in a reservoir, then this velocity head will appear also as the loss. As you look into it, that is the exit loss. So if you write the Bernoulli's equation here, then it appears at the velocity head. For example, if it is connected with another reservoir, and if you write the velocity head far end where the velocity is arrested, then it will be the exit loss there. So that means this will be the same equation we get whatever way we tell. So now this equation is solved and it is only a simple equation involving only K as the unknown. So we get the value of K as 8.8. That means the loss coefficient is 8.8. That means 8.8 into V square by 2G. This is the meaning of the loss coefficient, that the factor, multiplying factor with the dynamic head. Now, when the resistance is completely withdrawn, it is a child's job. This is equal to without any kV square by 2G loss. That means it is the frictional loss plus the velocity. That means if I write the Bernoulli's equation between this point and this point, the basic frictional equation is like that. And then sorry, we get the velocity of flow is 3.88. So the velocity of flow is increased from 3 meter per second when the resistance is completely withdrawn. Okay, any problem in this? All right. Okay. Now next, I like to discuss one very interesting thing, that sometimes that you will come across afterwards, that in case of a pump, for example, if a pump is fitted in a pipeline system, that means in the operation of the pump, let us consider the fluid is taken from this sump from a lower level and there is a pump. This type of problem, how you do solve? And let there is a pump which discharges the fluid, okay, into a reservoir. Which discharges the fluid into a reservoir, up reservoir, okay, the reservoir, overhead reservoir. How do you solve this type of problem? Now let us consider the difference between this reservoir is, this difference is H from the free surface of the lower reservoir, which is known as sump, and the center line of the pump from here, let this is H1. This also can be solved by pipe flow problem. This is a very interesting one. There is a pump in the, and intelligent students can get it. Now what happens? The purpose of the pump is to suck the liquid from lower level. The liquid is flowing from a lower level to a higher level. This is because energy is added here in the pump. Energy is added in the pump. So with the aid of energy addition, it is possible to take liquid from a lower head to upper head. That means the potential energy of the liquid is increased by virtue of the energy, electrical energy in the form of mechanical energy. External electrical converted to mechanical energy is imparted to change the potential energy of the fluid. That means the fluid at a lower datum head is being lifted. So this is flowing like that. Now let this tube is designated at S, suction tube, suction side of the pump. This tube is delivery side of the pump. By simple friction formula, you can find out this. You can do this problem. How you can do this problem? Let us see. Let us define a section here. This section is 1, and this is the free surface. Let us define a section here, that is let the section 2, and that is the final top surface, free surface. Now if I write the Bernoulli's equation between point, at any point here at this section, that is the entry to the suction, and at this point, what can I write? If this point 0, try to understand, pressure at 0, velocity at 0, and datum at 0. Why? Datum at, this is the datum. Not pressure at, I should not write 0, otherwise it will be confusing, because pressure here is negative pressure. Otherwise it will not suck from the atmosphere. So in this case, I induce the atmospheric pressure, Pa by rho g, plus velocity head is 0, plus datum head is 0, because I am considering the datum from here, reference datum. Then what is the head here? Let we define the pressure at P1 by rho g. This P1 by rho g is less than Pa by rho g. You can understand, because some other things will come. Because to create a velocity head here, out of the pressure head, atmospheric pressure head, this pressure head has to go lower than that. Obviously, V1 square by 2g. If V1 is the velocity in this point, that means in the pipe, if the pipe is of uniform diameter, plus H1. Now this is upon the center line, so inlet to the pump and outlet from the pump doesn't vary much in the elevation head as compared to its center line, in comparison to the difference in the head from the lower reservoir to upper reservoir. That is sump from sump to the overhead reservoir. So these changes are very little. So this is H1. So we define this as H1. That means this is the height from the sump of the pump center line, which can be taken as the height of the pump inlet and pump outlet. So this is the equation, plus all the losses in the suction side, that means sigma HS. So this is the pipe friction loss. Suction side, there may be a bend, there may be a valve, many things may be there. So all the losses encountered in the suction side. So therefore I am not posing the problem as such that there will be only frictional losses, depending upon the problem definitions. So there may be number of losses. So this is the precise Bernoulli's equation. Now if I write, well, the Bernoulli's equation from any point at 2 and a point at the free surface of the upper head or overhead reservoir, what we can write? We can write P2 by rho g, well, plus, please tell me, V2 square by 2g, please tell me, please, P2 by rho g plus V2 square by 2g plus H1, very good, is equal to, at this point again I have PA by rho g, a surface at the overhead reservoir, only understanding, then 0, then H, very good, then sigma HD, very good. That means all the losses encountered, this bend, and usually there is a valve in the delivery side. You will afterwards read in fluid machines course, valves are not placed in the suction side. So there is only a step valve in the suction side for some other purpose, for priming purpose, but there is no such valve in controlling the flow because of cavitation problem. Because now I can tell you, because you know this fluid mechanics principle now, because this pressure is suction pressure, obviously from this equation and physical principle also, that out of atmospheric pressure we have to create velocity and overcome frictional losses. So we should be careful about the losses, because velocity is fixed depending upon the capacity of the pump, flow rate of the pump. So we should be very careful of the losses, so that this pressure, so this quantity should be minimum, so that this pressure should not fall below the vapor pressure of the water at the existing temperature, so that the cavitation will start, water will boil off. So therefore it is very essential, I have told, in any fluid or any hydraulic circuit where there is a chance of pressure going below the atmospheric pressure or low pressure, that the pressure should not fall the vapor pressure of the working liquid at the working existing temperature. So therefore valves are placed in the delivery side only. So delivery side there will be many losses. So all the losses, including the exit velocity head, because I have not written the velocity head. You can tell me, sir, you are writing because I am using the same thing just I described in the last class. That means I am not taking a point at the delivery or discharge plane of the delivery pipe. I am taking a point at the free surface of the reservoir, just it discharges in the reservoir where the liquid has become stagnant. That means the velocity head, which could have come if I could have written the Bernoulli's equation at the discharge plane of the delivery pipe, it has come within the losses. That means the exit loss. So exit loss, bend loss, valve loss, frictional loss. If nothing is mentioned about any valve fitting, nothing is mentioned about any bend in a problem, so we will consider only the frictional losses if I know the length of the pipe and diameter of the pipe, but I will not forget to include the velocity head losses, that is the exit losses here. So now these two things shows us one thing, that if we subtract one from other or make PA by rho g equal, so what we get? We get P2 by rho. Now if I define just P2 by rho g plus V2 square by 2g plus H1, we defined as, well, already we have defined as H, no? H1 and H. Better we change this definition to Z1, I am sorry, to Z. The elevation is Z and Z1. It will be easier for me. Z1, I am sorry, Z1 and Z. That means I just change the nomenclature, that Z is the difference and Z1. Now if I tell that P2 by rho g plus V2 square by 2g plus Z1 as H2, what is this? Precisely this is the total energy at the outlet of the pump per unit weight. That means total head. Head means energy per unit weight. So total head at the outlet of the pump. Similarly, if I tell P1 by rho g plus V1 square by 2g plus Z1, which is the total energy per unit weight at the inlet of the pump, the total head at the inlet of the pump, H1. Then what I can write? Please tell me. So then I can write H2 minus Z minus sigma HD, which is equal to PA by rho G. H2 minus Z minus sigma HD is PA by rho G. That means H1 plus Z1. Some Z1 is missing. P2 by rho G plus V2 square by 2G, okay, plus Z1 is equal to, this is the Z1, is equal to Z1, no, this is H2, H2 means Z1 is included in the H2, well, H2 minus Z minus sigma HD, this is alright, is equal to
H1 plus sigma HS.
H1
Plus sigma HS.
H1 plus sigma. I am sorry, please help me. Alright, then we can write H2 minus H1 is equal to what? Z plus. Now this H2 minus H1 is the change in the total head from outlet to inlet. That means total energy per unit weight. That means this head is given by the pump. So pump head, if I tell that pump head is HP, which means the pump develops this energy per unit weight. This is nothing but H2 minus H1. So therefore this is the pump head, which is equal to Z plus sigma HS. And from a common sense, we can tell definitely, without knowing any even Bernoulli's equation, nothing, pipe flow problem, a intelligent student of class 10, if he tells that, if he is told this problem, he will tell yes, pump has to develop an energy which must balance or counterbalance or counterweight the energy equivalent to this height. That means the liquid has to be lifted, that means this potential energy is created plus the losses, and also to create the velocity, which of course is included in HD. So from common energy balance, people will tell the pump energy should be sufficient to overcome the frictional loss, to elevate fluid to this height, that means this potential energy plus the kinetic energy created by the velocity of the fluid, which here is included in the delivery losses, a component of the delivery losses, that is exit loss. So therefore from the physics point of view, this is clear. Alright, it means this is equivalent of telling that, this is equivalent of telling that there is a single line HP. That means it is equivalent of telling that there is a single pipe which simply elevates water to a height Z, by virtue of which, by virtue of some head given to it at this moment, this plane H. That means it has got HP. So if I write the Bernoulli's equation between this and this point, I will get HP is equal to Z plus sigma, because if I write total head is HP, which is given here, is equal to here Z, all other things 0, plus sigma H, which composed of sigma HD plus sigma HS plus sigma HD in the actual pump system. That means if there is a pump in between in a pipeline, we consider the entire suction and delivery pipelines as a pipe system where the input, because you will see that such a pipe system without any pump cannot make a flow from a lower level to higher level. But this is equivalent in saying that some energy is added. That means at this free surface we have extra amount of energy added to it. So this pump can be taken it here and can take the entire system as a fluid path or a fluid circuit where we have an energy here which will allow the fluid to flow up, and we can write this equation. The same equation, and this is the basis of developing the equations for a pump systems, which I will be discussing afterwards, which you will know afterwards, not now in this course, in the course of fluid machines. So it is clear to you? So I think today I will not discuss much, because next class I have thought I will be describing the concept of dimensional analysis, but I feel that today I must first give you a closure of this pipe flow problem. So, pipe flow problems are the practical problems where the flow takes place through pipes of circular cross section, but the flow rate and the dimensions of the pipe are such the flows are in turbulent region. In a pipe flow, the flow becomes turbulent in a fully developed pipe flow when the Reynolds number, you know, a dimensionless parameter defined as rho, the average times the average velocity, that is the flow rate by cross sectional area, times the hydraulic diameter, which is the diameter in case of a pipe of circular cross section, divided by mu, this dimensionless parameter known as Reynolds number, which is a symbol for the dynamic similarity, which represents the criteria for dynamic similarity, which I will discuss afterwards in case of flow governed by viscous force, inertia force and pressure forces. Of course, in a fully developed pipe flow problem, the viscous and pressure forces are the only dominating forces, since the inertia force is 0. However, we will come across with this thing afterward. So, Reynolds numbers, this dimensionless parameter exceeds 2000, and it has been found in all practical applications. The range of flow rate and the pipe diameter is such that the Reynolds number exceeds 2000. So, an analytical solutions of Navier-Stokes equations in closed form, which is known as exact solution, is not possible for a turbulent flow situation as such. But with the advent of computational methods or advanced numerical techniques, we can solve the turbulent flow situations with turbulence model. But all these turbulence models require empirical informations. These are based on certain empirical factors. So, therefore, we can tell even the advanced theories of turbulence based on experimental information. So, without going for such an turbulent flow analysis with turbulence model, where again we require empirical information, engineers in practice or in floor, they have developed a very good semi-empirical approaches in dealing with the pipe flow problems. In this view, I must tell you what an hydraulic engineer needs. He needs that if there is a pipe of some diameter and he has to force the fluid at certain rate, what should be the pressure drop over a certain length, and depending on which, what should be the power required to transmit that flow. Or you know what should be the power required, you know that this much power is available, you know this much fluid has to be fed through a pipe system whose length you know that it has to be transported over that length. What should be the exact diameter of the pipe, what diameter of the pipe you will select. So, these are the practical problems. So, these problems are analyzed by simple way of tackling the boundary Bernoulli's equations, modified Bernoulli's equations, provided you can identify the loss, different fluid losses in the fluid flow path. And these losses are defined through a friction factor or friction coefficient, Darcy's friction factor we have defined, and if we know the friction factor beforehand, then we can use the friction factor and solve this type of problems. And this friction factor is a function of Reynolds number in case of smooth pipe, or in laminar flow we have seen for pipe flow. In laminar flow conditions, that is Hagen-Poiseuille flow, friction factor is 16 by Re, or Darcy's friction coefficient or friction factor is 64 by Re, 4 times the fanning friction factor, which is the basic friction coefficient, shear stress by dynamic head. So, this friction factor is found for different ranges of turbulent flow from experiments, different empirical formulae, and they are nicely documented in a figure by Moody, known as Moody's diagram. So, we employ Moody's diagram, find out the friction factor. Sometimes the friction factor may be given, sometimes the equations may be given, friction factor relating Reynolds number, from which you find out, and we solve the problem with the help of friction factor and the modified Bernoulli's equation. This is semi-empirical approach of solving the pipe flow problems we have discussed. Next class we will be discussing the principle of similarity and dimensional analysis. Thank you.